Calculus, video 52, optimization, example 1. I guess technically we had an example in our first optimization video, but we'll call this example 1 anyway. So example 1, beginning with a 24-inch by 18-inch piece of cardboard, cut squares out of each corner. So you're cutting square out of all four corners of your rectangular piece of cardboard. And then you're folding up the remaining sides to make a box with no top. And the question is, what is the maximum volume that can be created like this? So a picture, I'm sure, would be helpful here. So we have this rectangular piece of cardboard. Actually, pause the video, write down the question, and then we'll come back to the picture here. Okay, so we have this rectangular piece of cardboard. It's 24 inches by 18 inches. And what we're going to do is cut squares out of each corner, something like these red squares here. And it's important that they are, in fact, squares. Then you'll take and fold along these dotted blue lines. Here, 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 here. Right? So you'll take what's left over and you'll fold along those dotted blue lines, and you'll get something that looks like this. So those dotted blue lines are here now, and now we get a box. Right, we'll fold these up and create a box that looks something like this. Now that box won't have a top to it, it'll just be a bottom and then the four sides. Okay, the question is, what is the largest box that I can create like this? All right, what is the most volume that I can fit inside of my box? All right, not a bad idea. If you want to go ahead and think about it, try your own way first and then come back and restart the video and see what we do here. I think one of the best things to do is to start getting some variables onto our picture here where we can. So things we know, things we don't know. The only thing we know right now is we have a 24-inch along the bottom, 18 inches along the side for the length and the width. And then we know we're cutting out squares in the corners. Since we're cutting out squares, we know that if I call this, say, x right here, that length of square, that length on the square, that this length here is also x, because it's a square, so it must be the same on both sides. The question is, how big of squares should we cut out? Right? So if we cut out really small squares, then when we fold that up, we're not going to have much height to fold up. The base will be bigger, but as I fold those edges up, if I only cut out a very small square, then I'm not folding up very much for the height. So a larger base, not very much height. If I cut out bigger squares, that's going to give me more height to fold up along the edges, but it's going to decrease the base, that dotted blue base that I have there. Let me see if I can draw that picture. So if I decide to cut out small squares, right, something like this, then the base that I have left over will be quite large. But if you fold these up, you're getting a box with a very large base, but a very small height. Okay, something like that. If instead you cut out larger squares, let's say we cut out, fairly large squares like this. Okay, now the base is quite small here, a very small base, but my height is quite a bit bigger. So now my base looks like this, a very small base, but my height, that may be too much. It disappeared on me. I'll try that again. Not the best looking rectangle box, but you get the picture. You have a very larger height there. My guess is it's somewhere in between these, where you want to cut out enough rectangle squares, a large enough square to where you get some height for your box, but not so large that you end up making your base too small, where you have a larger height, but the base is smaller. Didn't like my picture. I'm just going to try drawing it one more time. Anyway, something like that. Okay, so the question is, going back up here, what should what should the size of x be that we're going to cut out of squares of each corner to create the box with the largest volume? So we're going to maximize the volume of the box. So we're always going back and saying, what am I trying to maximize? What am I trying to minimize? I'm trying to maximize the volume of the box. So that's going to be my equation. I need an equation that maximizes volume. So if I have this box here, what would be the equation of a volume? Volume for a rectangular box is length times width times height. Right? That is not length and width and height. Hang on. You ever draw these boxes in 3D and then they kind of go away? There it is. We've got the length here, we've got the width here, and we've got the height, say, here. It flips around sometimes on you if you just stare at it. All right, so length, width, and height of the box. So volume, we know, is length times width times height. That's what we want to maximize, but I have an issue here in that I have a variable L, a variable W, and a variable H. I don't want to have 3 variables over there, I only want 1. And those really are variables. The length of the box will change depending on the size of x, the x square that you cut out. The width of the box will change depending on the size x that you cut out, and the height of the box will change depending on the size x box that you cut out. Therefore, all of those really are variables. The idea here is actually not that we write volume in terms of length or width or height, but we're going to go all the way back to x. We're going to write everything in terms of x over here. But maybe first, let's go ahead and get our bounds, our endpoints, if you will. Probably not going to be the answer here, but let's see what happens. What is the smallest that x can be? What's the very, very minimum value that we can cut out here? Technically, it's anything more than 0. So we're just going to say the x has to be greater than or equal to 0. I mean, 0 gives you a volume of 0. You cut out nothing. You have just a base, no height. Okay, what is the maximum that x can be? This one's a little trickier. The maximum that x can be is going to be limited by this side of 18, by the shorter side. So over here I have an x. If I just put all the x's on there, right? That box is a square there. The square on that we're cutting out. So I have x's on every side. And if I make the one down here, x's on every side since it's a square. The total length is 18, but as I cut out squares from every corner, I'm cutting out an x from up top here. I'm also cutting out an x from the bottom here. And so I'm really taking off 2 x's from every side. You'll see that on the 24 side length as well. I'm cutting out an x from right here. I'm also cutting out an x from right here. I'm decreasing the 24 inches by 2 x's. I'm decreasing the 18 inches by 2 x's. So the maximum that this can be is x is equal to 9. How do I get 9? Well, if x is 9, then this first x will go all the way from here to here. That'd be a 9. And the second x down here would go from here to here. That would also be 9. So the most that x can be is 9. The least that it can be is 0. But let's say x is 9. What happens to the volume? What happens to our box? If we cut out 9, an x of 9, I'll probably erase this in a second, we get a box, we cut out a square that looks like this, and this, and this, and this, and all we have left is just the center thing with nothing to fold up, right? There's no base there, and so we end up with, again, a volume of 0. So the endpoints here, x is 0 and x is 9, give us kind of our constraint. We know that x must be between 0 and 9. However, if it's either one of those, we end up with a volume of 0. So those will end up being the absolute minimums. We want the absolute maximum. How can we replace, going back to our equation here, volume is equal to length times width times height, how can we replace a length in terms of x? How can we replace the width in terms of x? And then what is the height in terms of x? Okay. So I'll call the length the side with the 24, I'll call the width the side with the 18, and the height is the part that's being folded up, if you will. So after I cut out the 4 squares from each corner, what will be left of my length? So I'll start with 24, I'll cut out an x from the right hand side, I'll cut out an x from the left hand side, and my length is going to end up being 24 minus 2x. Same thing on the width. I start out with a width of 18, but I'm cutting out an x from the top and an x from the bottom, and my width ends up being 18 minus 2x. That's why the x's at most could be 9, because that would make a width of 0. Okay, how about the height? The height is, we're going to take each flap here and fold it up. So like the height is, I have this flap here, and the flap here, right, and we're going to, and the flap down here, and the flap over here on the side. And we're going to take each flap and we're going to fold it up, and that becomes the height. But if you look, that is just a distance of x, right here. That's just a distance of x. So the height is however much is folded up. We get a height equal to x. So we need this, we're going to use this, we're going to use this, and we're going to replace all those in that volume equation so that everything is in terms of x. It's going to look something like this. Volume is length times width times height. The length was 24 minus 2x, the width was 18 minus 2x, and the height is x. Multiplying those together, we get volume is equal to, I'll just distribute the first ones here. The 24 times the 18, the 24 times the 2x, the negative 2x times the 18, and negative 2x times negative 2x, and then we'll multiply the ending answer by x. So 24 times 18 is 432, minus 24 times negative 2x, negative 48x, negative 2x times 18, negative 36x, and then negative 2x times negative 2x plus 4x squared. All still multiplied by x. So we have volume is equal to 432 minus 84x, putting these two together, plus 4x squared times x. So volume is equal to, I'm going to rearrange the order here. I'm going to multiply the x by all of these, but then switch the order and call this 4x cubed minus 84x squared plus 432x. And we are happy. We are happy because we now have a volume equation, the thing we're trying to maximize. We want to maximize volume. Right, that's what we're trying to do. And our volume equation is now in terms of one variable. We've already checked out the endpoints. We know that if x is 0, you get no volume. If x is 9, you get no volume. So it must be between 0 and 9. Now we can just take the derivative and check out the relative extrema. So when is the derivative equal to 0 and when is it undefined? We have a polynomial here, 4x cubed minus 84x squared plus 32x. So the derivative will never be undefined. So really, we're just trying to see when is the derivative equal to 0? Question mark. Well, what is the derivative? I guess I should start there. The derivative is equal to 12x squared minus, would be 168x plus 432. So the question is, when is it equal to 0? And when is the derivative undefined? It is never undefined. That is a quadratic. Equal to 0 whenever 12x squared minus 168x plus 432 is equal to 0. And I could try to factor or quadratic formula, but let's see if any of those numbers divide nicely and simplify this thing. Let's see, 168 divides by 12. 432 divides by 12. We can factor a 12 out of all this. So let's go with 12 times x squared minus 14x plus 36 equals 0. This thing will equal 0 whenever x squared minus 14x plus 36 is equal to 0. Let's see, that would be nice if it would factor 36, 1, 18, 2, 12, 3, 9, 4, 6. Nope, I'm not seeing it's going to factor, therefore let's go ahead and use the quadratic formula. Right, here A is 1, B negative 14, C 36. So to solve for x, we use the quadratic formula, negative b over 2a, plus or minus the square root, b squared minus 4ac over 2a. All right. That is equal to positive 14 over 2, plus or minus the square root of 14 squared should be 196, negative 14 squared also 196 positive, minus 4 times 1 times 36. Over 2. So x equals 14 over 2 is 7 plus or minus, let's see here, 36 times 4, 144, 196 minus that, 52. That would be 7 plus or minus. 52 breaks down into 13 and 4, so let's go square root of 4, square root of 13 over 2. That's 7 plus or minus 2 root 13 over 2. That means we get x equals 7 plus or minus the square root of 13. Okay, that's two answers. Let's check them both out. Let's check out x equals 7 plus root 13. And x equals 7 minus root 13. And I should probably do approximations here, so I'll get some decimals. 7 plus the square root 13. I've got 10.606. Is there a problem with that answer? Yes, there's a problem with that answer. Go back up to the top. 10.606. If x is 10.606, what's happening is that's 10.606, that's bigger than 9, and then x on the bottom here, 10.606, that's bigger than 9, that's going to cross over, that's two x's there, 2 times 10.606 is more than 18. You can't take out 10.606 from each side, on top and bottom for each of those squares, so that answer doesn't make any sense. So, remember the constraints there, the bounds, was that x is between 0 and 9. It can't be more than 9. It can't be 10.606. So, we'll cross that one off. Now let's do 7 minus the square root of 13. 3.39, 3.394, 3.39 will probably be good enough. 3.39. Okay, so this is the value of x that will maximize the volume of the box. However, I think we were in inches here, if I'm not mistaken. That's not what the question asked. It wasn't what is the value of x, it was what is the maximum volume. So we need to go back and actually find the maximum volume. Two ways you could do that. You can either find L, find W, and find H, and then plug those numbers in. That's not a problem, right? You're just plugging the 3.39 into the x's here. So 24 minus 2 times 3.39 gives you the length. 18 minus 2 times 3.39 gives you the width. H equals 3.39, that gives you the height. You multiply them all together, you get volume. That's one way to do it. The other way is we already have a volume equation right here that we're trying to maximize. Simply plug 3.39 into this equation will also give you the maximum volume. I'll go with that route. So I've got 4x cubed minus 84x squared plus 432x. Volume is 4x cubed, I've forgotten, 4x cubed minus 84x squared plus 432x. And I would like to know what is the volume at 3.39 approximately. So plugging that in. I'm getting 654.98 approximately cubic inches. Maximize the volume of the box. Okay, very good. There is another sort of extension on this problem, and we won't work it in here, but just so you've seen it before. So what happened was this time we took our rectangle, our 18 by our 24 inches here by 18 inches there. We cut out a square from the corner, from every corner. And we got a volume equation, right? Volume is 24 minus 2x times 18 minus 2x times x. And then we multiplied that out and took the derivative to find the maximum. The second part of this is, from this first part, we created a box, right? We had this sort of box here, and it had some height. And we're looking to find the maximum volume of this particular box. The second step is you take that box and you add it to the box that you can create with all of these squares. So if you take these squares and you actually cut them out, right? So this square here and this square here, and you make a box with the squares where it has no top and no bottom, and so it just looks like this. You've got this box. Right, but that box has no top or no bottom. It just has all four sides from the four squares, but you can find the volume of that box. The volume of that box would be x cubed, because it's just a bunch of x's, right? It's created from these four squares, which are all x's. And so you get this other box. You add the two boxes, and you're asking yourself now, what is the maximum volume of the sum of those two boxes? Well, it's actually not that hard. You basically take this extra box that you create with the volume of x cubed, add it to this volume equation here, and then take the derivative and find the maximum. You can try that one on your own.